right, so a couple things to note. This will take about 15 to 20 minutes, and then the rest of the time will be devoted towards you guys working on your stuff. No quiz today or this week because there is a timed lab, right? So I figured that was, you have enough to get on with. You'll probably have another quiz or two next week just to get, make up for that. But this week, you guys got a timed lab. So first time lab for you guys is Thursday. So what does that mean? You guys can, basically you're going to be going over more array list stuff, right? So the stuff that you did for week 2, right? The array list questions, that's what you're going to be answering. Not so much the stuff on week 3. So the questions where you have to go through array lists or lists in general and just manipulate them, be able to do that. So if you feel comfortable now with being able to do the stuff you did for the array list, then you should be able to be comfortable with the stuff on the timed lab. The timed lab is about 3% of your grade. It's like 3.3% technically, because because there's 3 timed labs each, and they are 10% of your grade. So it's like a mini exam. The difference here is you get a bit more than you normally get in an exam. So first off, what resources are you allowed to bring? And the answer is whatever you can bring. So it's easier actually to say what is prohibited. What is prohibited is hopping onto Google or some other search engine and essentially searching for code. Okay? Essentially, if you can use it electronically, if it's already on your computer, you can use it. If it's on Canvas, you can use it. If you can get to it from Canvas, you can use it. Okay? Makes sense? But no going on Stack Overflow to do that, to go and, find your answers. However, going to Stack Overflow beforehand, downloading basically a bunch of pages from Stack Overflow and having them for reference, because you think they'd be good notes to have, totally allowed. Going to those pages, downloading them, printing them out, totally allowed. Because preparation and knowing where to find information is key, right? So I like that to be able to be reflected in that. Of course, it is open book and open note. So essentially, it's just like you would be able to just like you would work on homework normally, with the constraints of you can't talk to other people and you can't go online to search for an answer. And just definitely can't go to Fiverr and ask, hey, somebody, answered this question and I'll pay you $5. Definitely not that. Okay, so the timed lab, you've got a lot of resources, and I'm not making it more difficult because you have more resources. I'm letting you have your resources there to help you get through that. Now, the exam itself, depending on what question, not this week, not next week, but possibly week 5. At the earliest, that one, depending on what questions I have, you'll either get nothing or a cheat sheet. Okay, that just depends on what questions I ask. Okay, and the nothing sounds a lot more scary than it is, but I'm getting ahead of myself there. So this week there will be very little coding unless you work on this extra credit that I gave you. Now this extra credit has no due date that's set. Technically, but of course, to receive credit for it, you do have to, complete it by the time final grades are due, right? So this is worth 10 points, okay? Each page is worth 5, but this is incentive for you to learn regular expression, which will crop up a couple times and be very helpful if you learn them, but they're not necessary, right? You don't have to learn them, but they're useful. Also, because regular expressions are pretty much useful in any programming language, their implementation's kind of language agnostic. You're allowed to use any programming language you like, or you could use grep, basically parts of, bash. You can use basically those tools. I don't really care how you do this, so long as that you solve these regular expressions. So I provided a text file called words.txt. You'll have to read that file somehow and go through it. And these are questions that you just need to answer, like, I like animals. How many words? So words.text, by the way, is like a a dictionary used for spell checking by a computer. I like animals. How many words contain the word cat or dog in them? 4-letter words are supposedly naughty. How many 4-letter words are there? So how do you write a regular expression that searches for 4-letter words, right? How many do more words end in ing or ion? Which is a question, right? You can search for any word that has ing in it just by using Control F. But how do you just search for a word that ends in ing? And the answer is you have to use regular expressions to do that. All right, and these are all solvable with regular expressions. I provide a link where you can learn how to type up regular expressions. There's also a lot of good resources there. But again, you can do this in any programming language that you choose. You just have to click on the link provided. And then this other page has more regular expression questions, 3 of them specifically. All right, so that's the extra credit. So just to keep you busy in case you need more work, but also good incentive to learn. So this is what we are working on. This is your lab for the week. So let's start from the bottom. You can turn this in basically any way you want. You can hand it to me or TA, like print it out and hand it to me. You can print it out, scan it, or take pictures of it, upload those onto the web page, onto Canvas, and that's great. You can just type up your answers and upload that. We are pretty much format agnostic here as far as how you get the answers to us. Okay, this more resembles a math worksheet than coding. Okay. Here are the basic rules for that I've put on. This is front matter that I haven't put on this assignment before. So, but this has to do with all the summary of the rules for calculating big O notation, the algorithmic efficiency of an algorithm. So how many of you have been able to watch some of the videos on big O notation, right? A couple of you. It's okay. I posted them very late. I posted them fairly late, like in the afternoon on Sunday, so it makes sense if you didn't get the chance to watch them yet. And that's fine. But that's the stuff you'll need to watch if you want to do this homework, okay? And it's a fairly, this is actually, especially this first page, will be some of the easiest math you'll ever have to do. But essentially it's saying what we're looking at is that we need to start looking at how data structures compare things, right? Some of the problems that we did, like, take the our unique problem that you had to do in your homework, for instance, right? Doing that with a list, right? Doing that one way is, if you're going through it so basically if you're going through and checking every item against every other item, that's going to take a certain amount of time. It's actually going to, as you'll learn, take O of n squared time. That's probably the way you did it. If you if you sort that list and make sure that basically no 2 adjacent things are the same, then that takes n log n time because you'll find out that sorting algorithms are n log n. But if you know to use the right data structure and use a set, you can go ahead and use a set, and adding and removing things to sets are super quick. So you can actually perform it much quicker with the cost of using up a lot more space. So what are these things I'm talking about? We're talking about ways to evaluate the speed or the efficiency of algorithms, okay? Now, as I mentioned, there are 3 resources we concern ourselves with when we're analyzing what computers can do. We look at time primarily, and then the other 2 are space and energy, right? How much memory does this computation take up? Or energy, which is like, okay, how much battery power am I expending? Which is very useful, like if you're going and planning on doing any kind of mobile device programming, or the big research aim for that still is military applications for dropping small wireless devices that don't need power, right? So that energy cost has always been a consideration in more specialized areas. But time is the most important of all for analysis. From a practical standpoint, you cannot buy more time. You can buy everything else. You can buy a bigger battery pack. You can buy more RAM, right? But you can't buy more time, right? You might not be able to fit more RAM or a bigger battery pack in, but you can't. But there's an option, right? You can't buy more time. Okay. So, and the other thing is, on the more user-friendly side, you know, if a program takes forever to load, nobody's going to use it because it just feels terrible to use that. Like, I mean, you could probably get annoyed with a web page after 3 seconds. That's the average amount of time people get fed up with a web page loading. So now when we're analyzing time, of course, because my computer works differently than your computer, we can't really like just say, oh, it takes X seconds on my computer or Y seconds on yours, because there's going to be differences in time based on processor implementations. Also, you know, running a program, as you see in the videos, it takes different amount of times just based on when I decide to hit my buttons. Up to like tens of milliseconds of difference, which is a lot for a computer, just based on how things are being scheduled. So, instead we use a mathematical notation called big O notation, and we become very familiar with 3 different types of algorithms, or 3 different types of runtimes. O of 1, O of n, and O of n squared. The first one is constant. The second is linear. And the third we call quadratic. Okay, so what do these mean? Basically, they say how given something of size n as our input, right? So like an array with n items in it, or a list with n items in it. How quickly is this problem going to grow in the amount of time it takes? Now, the easiest example of that is a constant time algorithm, which does not change based on the input size. Okay, O of 1 means that it will not change based on input size. So like the classic example I use is returning the size of a list, right? Because that's just a variable stored, stored in a list, right? That's a 32-bit number, and it doesn't matter what the value in the 32-bit number is, right? It doesn't matter how many ones are set, how many of the bits are set to 1 and how many are set to 0. It's going to take the same amount of time to return 100 and 1 million, right? No change in time to return that value. Doesn't matter how big the list is. And so constant time algorithms, they're agnostic in terms of the size of the list. Linear size are fairly intuitive to understand. It means if I have one more unit, it means that if I have one more item to process, I have one more unit of work to do, essentially. Or maybe 2 more units of work, or maybe 5. And if I add another item, it would be another 5. And if I add another item, it would be another 5. But it's not going to vary, right, is the point. I'm going to just erase this here. You know, if we were to graph that out, right, with n over here and the amount of time it's going to take, right, the relationship would look like this, or like this, or like this. I'm not really caring about the specific slope of the line or the offset of the line. I just care that it is a linear relationship, right? It fits the format of mx plus b, right? Okay. The example I would like to use that's very practical is, or very real world, is like me. I say I've got a classroom with 20 students, right? And that means come exam time, I have 20 exams to grade. If I have a 21st student, that means I'll have one more exam to grade. Or I could look at it as now I have, 20 more questions to grade because the exam was 20 questions long, right? So, but the point is that if I add another student, that would be another 20 questions. It wouldn't magically bring the number up to 40, right? So one more student equals one more exam. Another student equals one more exam. A student who enters, who enters my class, they aren't going to be bringing 3 exams worth of work with them. They're going to be bringing 1 exam worth of work, right? Okay. An O of n squared algorithm, on the other hand, is when adding another item of work impacts all the other things I have to do. It's where I have a quadratic relationship. So it's going to look like some parabola, right? It could look like this, or this, or this. I don't care the particular shape of the parabola. I just know it's going to look like a parabola, right? O of n squared, to use up our exam example again, that's where I've got a, that's like, say I've got a student who, I'm very cautious because I notice a couple of questions from some students that are very similar. So I start getting really paranoid and I compare every single page on every single exam, pairwise, right? So for student A, I compare all of his answers to student B. Then I compare all of his answers to student C, then student D, and so on. And then I do B and C and D and E and F. Then I do C and D and E and F, right? And so on and so forth, right? So I have 20 students, right? And now if I add a 21st student, that means I have to check 20 more pairs, right? Right? The 21st student means I've got this 21st student, there's 20 other students to check him against, right? Adding a 22nd student would mean I have 21 more pairs, right? So adding this nth plus 1 student adds n more work for me, right? That makes sense? Adding one more student means I have to do, another batch of work. Typically these algorithms, they look like, oh, you do have to do one, adding your first time, you get 1. Adding your second one, that's 2 units of work. Adding your third one, that adds 3 more units of work, and so on and so forth. And you'll find that in my videos, or if you've taken calculus and remember series, that's going to give you a quadratic relationship. So typically though, so the question is like, okay, given an algorithm, how do I look at an algorithm and find out, surely, this sounds very hard. Surely there's an easy way for me to just kind of glance at an algorithm and instantly know it's runtime. But that would be too easy, right? And the answer is rule number 3, counting the number of nested loops usually works. That works like 9 times out of 10 to figure out how complicated the algorithm is. This fails when we deal with recursion, right? But normally this works. Now it gets a bit more complicated when your method, say it has a for loop and it calls a method, right? You have to then check, does that method have a for loop inside of itself, right? But I have faith in you. It's not that bad. So for example, suppose I have some method, right? And I suppose I should be recording like this. Suppose I have some method, right? Method that takes in a list L, right? And I'm just being very loose with the syntax here, right? Method that takes in a list L, right? And suppose it takes in a list, and it does one thing, and then it does another thing. Maybe it takes the last item in the list and the first item in the list and subtracts them or something like that and returns an answer, right? It doesn't iterate through all the items in the list. It just kind of grabs 2 items that it knows where to find them, and it's done, right? It doesn't matter what the size of the list is in these cases. The first item and last item, those are fairly easy to figure out, right? Okay, that's a constant time algorithm, right? Because it doesn't depend on the size of the list. Okay, on the other hand, suppose I'm summing this is a list of numbers, and I sum all the list of numbers, right? Right, so I have a for loop that goes through everything in the list exactly once. This is then this is what we would call a linear algorithm. It is O of n, and how many for loops are there? Like how deep does it go? It only goes 1 deep, so it's to the first power, which we normally just leave off, right? So it's linear time, right? Suppose we're doing the unique problem that we were doing for homework, right? Where you're going through and you're checking every pair, right? So that's the way you probably wrote that is that you had 2 for loops in there. One that goes through all the items, and this inner one goes through all the items, or maybe almost all the items, right? Right? It maybe does n the first time, then n minus 1, then n minus 2, and then there's really not much to check as you get to the end if you optimized it, right? But it's too deep, and it goes through all the items, and each of them go through go through n items. So it is O of n squared, right? Because there's two nested, right? The loop goes too deep, right? What about this? What would if this also goes through all n items, what would this be? O of n cubed, yeah, O of n cubed. Now, typically, the archetypical example of this is actually matrix multiplication, but for right now, we're just dealing with like but this pretty much this rule over here gives you pretty much all the. It gives you pretty much an easier way to figure out all those polynomial time ones, all the ones that look quadratic or cubic, or the curves above that. But typically, we don't go more than 2 leaps deep. Most algorithms don't require that. And typically what happens is that we do some analysis, and we get these, and we do this analysis, and we say the time this algorithm takes based on input size n, right? It has to do like n cubed steps plus 5n squared steps plus 1 million steps, right? And then basically we do this analysis. We count up the steps they have to take, like this algorithm has to take, right? These simple operations that they have to do, be it checks or additions or assignment statements. And what we do is we can take this and turn it into a big O of time to say how quickly this is going to grow. Now the idea here is that we only care about the biggest degree of n. So the biggest degree here is n to the cube power, because as n gets to be a supermassive number, like 100 to the 100th power, or 10 to the 100th power, right? This is going to be 10 to the 300th power, which is 1 followed by 300 zeros, versus 10 to the 200th power, 10 followed by 200 zeros. When we're talking like a difference of 100 zeros, we have, our minds are just not built to deal with that kind of difference in numbers. But this is an error, essentially, in terms of like the significance it has, right? It makes no difference. So once this gets to a massive enough number, these other things just stop mattering, okay? And the other thing is that the constant factors don't matter, right? 500n and 5/1000 of n are both O of n, right? They're both a linear relationship, so we put O of n. And the other thing is that these typically describe like the worst case scenario that we're going to get. It's going to be no worse than a linear relationship. Sometimes we get lucky and we run it and it goes like that. But sometimes it's worse. But sometimes it's bad. But it's never going to be worse than a linear relationship. Okay. So the first page. So each of these pages are about 20 points. The first one is just taking these fake times that I've come up with and giving me an answer. Write down like O of something in there. And big thing for this homework. Come to me, and you can always come to me and ask me if it's right, and I'll tell you whether it's right or you need to go back and fix it, right? So there's no reason why you guys shouldn't get A's on this one, okay? Second page is analyzing the array list. Third page, or is that all that? Yeah. So the third page of work, rather, is analyzing this algorithm. Here's a question about space complexity, which I don't go over. You're going to have to kind of work through that on your own and figure out what is space complexity. And then what is the time complexity of this algorithm above. And then this other page over here, it is analyzing BOGO sort. Now, BOGO sort is one of two algorithms, the other being stooge sort, that don't exist in the wild. They only exist in an academic setting for you because BOGO sort is terrible and stooge sort is kind of terrible. Not completely terrible, just kind of terrible. But they exist for the purposes of analyzing algorithms. So BOGO sort, just to summarize, its sorting algorithm is while the list is not sorted, shuffle it randomly. Okay? So once it's sorted, right, then we're done. Right? So it's essentially throwing a deck of cards up in the air, gathering them up, and hoping they're in the right order. Now, as you imagine, this might take a long time, but thanks to big O notation, we can actually quantify how long this is going to take on average, right? Then I ask you like, what's the worst case runtime? And I accept a lot of answers for that. Because I don't like there's philosophical debates about that. And what's the average time and why? And finally, for your last 20 points, go over the items you wrote go over the things you wrote in Lab 2, okay, for the array list assignment, and figure out the big O notations of those. And I'll give you a hint, right? I put 3 different times up there: constant time, linear time, and quadratic time. Your algorithms are going to be one of those 3, and I guarantee they're not going to be constant time. Okay, so that should make it fairly straightforward to figure out. All right, and that will be good practice also for the exam, because on the exam, typically when I have you write a method, not the timed lab, right? None of this is coming up on the timed lab. On the exam itself, I typically have, like, for every single time I have you write a method, there will be a 2-point question right on the bottom of the page that says, what's the big O runtime of your algorithm or the method you just wrote? Okay, so that'll be good practice for that. All right, so you guys can go ahead and get